Thanks for coming to my talk about quantum sensing for materials testing. I know the talk was announced in German, but actually I grew up close to the Swiss border and I speak quite a vicious dialect, which makes my high German not very suitable for this occasion. So allow me to switch to English, please. So I'm from Fraunhofer IWM in Freiburg, and the results I'm going to present here are all sort of done in a collaboration with two other Fraunhofer institutes, namely the IAF for Applied Solid-State Physics and with the IPM for Physical Measurement Technologies. So let me guide you through the outline of what I'm about to show you. The talk will be parted in like three main parts. We're going through how we go from a macroscopic scales to meso and micromechanics, which holds sort of some advantages. In the second part, I want to show you some recent results that we do with magnetomechanical testings with optically pumped magnetometers. And in the third part, I want to show you the results we did on quantum sensing with NV centers on our microtensile tests. I will, of course, give you a short outlook and a summary in the end. So let me start up with how we see any signal. So I will start with the mechanical testing. Typically, if you go for a mechanical testing procedure, we usually have some sort of material and we just apply a strain, so we pull on it and we measure the force that is applied and divided. We take the force and divide it by the area of the sample cross-section and we get the stress, so we have a classical stress-strain curve. So this is the quasi-static tensile test, which is characteristic for technical materials. We have, of course, like the Hooke's law in the beginning, which gives us a Young's modulus, and we go to a plastic deformation and then to fracture. So now people have found out if we pull on a material and it is ferromagnetic, we end up generating a magnetic field. So how do we do this? It's called the inverse magnetostrictive or the Villari effect. So if you look at this material if we have like zero strain, this should be an epsilon. I got killed with my phones. So if we have here zero strain applied, we have all the magnetic moments in the material basically randomly oriented, showing every position and cancel each other out to zero field. Now if we pull on this material, we apply a strain and elongate the material piece, we generate a magnetic field because all the magnetic moments in the sample are lining up. So, and at some point we also have a plasticity if we reach this area here in the strain curve. This changes the structural integrity of the material, which also changes the magnetism a little bit. So if I'm talking about cyclid loading and fatigue tests, for example, we apply strains which go up the Hooke's law and we go basically little bit across the yield strength, so in this area. Okay, let me show you first what is happening in literature because it will be sort of relevant. There's a group by Bauer et al. Who do this very extensively. They have a lot of papers on these topics, and they typically use material samples which are sort of long. So these things are 20 centimeters long and 2 centimeters wide. You can see this thing here clamped in the middle of these two poles. And they measure the extension here with this extensometer, and the magnetic field here is measured with the classic sensor with the so-called flux gate, which is aligned here on the side. So what do they see? If you look at this graph here, you can see in black the stress as the number of loading cycles, which follows here this certain pattern. And in red, you can see the magnetic field that is measured along. So the magnetic field here really follows the stress circles. So now there are certain things that we can see. First of all, we have this rise of the magnetic field in the beginning, and at a certain point you have these dents that are evolving on top of these stress amplitudes. This is called a Villari reversal, and this is sort of a very typical effect when the strain that you apply becomes dominant in the end. So now, as I said, this is done on very macroscopic samples, and this holds, of course, a sort of drawbacks. You need a lot of material, you need large samples, and also the fatigue is usually a little bit more statistic. You have maybe certain areas where cracks are forming, and it's all a little bit not very in a controlled way. So what we do in our group, we use very small samples. Like as you can see here, this is a typical tensile test sample that we use. So it's all fits on sort of a very small coin. This holds a certain advantage, namely the volume of these small tensile test samples are so small that we are in the region of a technical crack, which means if this thing breaks, it breaks at exactly 1 point. This gives us the opportunity to have a high degree of control, and we can compare many experiments with each other because we only have one damage point. Of course, one drawback is that we have very small magnetic fields generated now, because the strength of the magnetic field here scales with the volume of the sample. But fortunately, as given by the name of the exhibition, we have quantum sensors to solve this problem, which are very sensitive, and we can see these very small magnetic fields. If we have here the magnetic sensitivity and the spatial resolution, I think these sorts of plots will be known to most of you. We have, of course, on the one end, we have the diamond and V's centers magnetometry, which give us a magnetic field sensitivity of a few nanoteslas and a resolution of down to a few nanometers as well. So on the exactly opposite, we have the optically pumped magnetometers, which give us really, really high sensitivity of a few picotesla, or tens of picotesla even, but a resolution which is only the millimeter area. Now our tensile samples actually fall right in the exact middle, which is gives us the opportunity to use both of these technologies on one sample. So what is our vision with this? We want to detect material fatigue or microstructure quality, like precipitates or microcracks, and we also want to find new fields of application at many different length scales, meaning we want to go to like components where we cut these certain little microsamples out, but we can also go from a top-down process where we cut a sample and destroy it to a bottom-up process where we can maybe use focused ion beam induced deposition of cobalt to gain structures which we can maybe strain engineer to have higher gradients for quantum technologies, which is sort of like a future perspective of what we want to do with this experiment. Okay, in the talk here, we use two different materials. One is an iron silicon, the other one is pure iron. Why do we use exactly these two? Iron silicon, as you can see here on the scale bar, has really, really large material grains, actually like in the orders of centimeters, which allows us to cut monocrystalline samples out of a single grain of the material. Also, iron silicon is very well known for the magnetic states. It's like a transformer steel, electrical steel, very much research done in it. And pure iron has like this microstructure involved, so we can actually have a look at what influence the microstructure in the material has on the magnetic signal. Also, you can see here the scale bar is much smaller. So we have small grains. The samples itself, we have like here this small gauge area, which is 600 micrometer long, and we have 400 micrometers in width, and the whole sample is like 250 microns wide. We have here these triangular shapes, which is actually a clamping area where we hold the sample down, and the part in the middle is where we do actually our test. Then we have this curvature, which is also interesting. This is designed in a special way with several radii of curvature, so that the stress that we apply is really uniaxial in the middle. Then we transfer this pattern on top of our, in this case, iron silicon material, and then we cut it out with an external manufacturer with microwire erosion. So the setup that we use looks as follows. We have a tensile test apparatus here going through, and this is a magnetic shielding, actually one that we designed freshly at Fraunhofer together with Segels, which is a company which builds these things. We have piezo and a motor and a loading cell, like force measurement cell. And if you look inside of the shielding, we have a coil system which is used to suppress residual magnetic field gradients. And we clamp this sample here in the middle, and here is the OPM sensor. And when we pull this material apart, we generate the magnetic field, which is measured here. And on top of this, there's a camera in which we can measure actually the strain on the sample in a completely contact-free way by using a digital imaging correlation program. The sensor itself is a commercial product by the company QSpin, which is located in Boulder in Colorado. It's a spin-off with Svenja Knappe, who's also working with IPM at the moment. And these things are really handy. They're small. You can just it's a plug-and-play system, and it has a noise floor of 0.01 picotesla. So you can see here the 60 hertz line in the US, and this is like a really, really sensitive system, which usually used to measure brain currents and stuff like that. So now we have the microsamples, we have the super sensitive sensors. What do we see? If you use these things together, this is data from us, from our institute. We have in black again the stress as a function of time, and you have in red the magnetic field as a function of time. We can see the magnetic field follows the curve. As a reminder, that's what Bauer sees in the literature at huge samples. And if you look at the magnetic field scale, we go here up to 800 nanotesla, and we are a factor of like, what is that, 400 smaller? And we can still see that like it's 1 to 2 nanotesla actually. So we can actually reproduce the state of the art on macroscopic samples with our microsamples and these OPM sensors. To summarize part 1 for you, the Villari effect is used for magnetomechanical testing. The results in the literature are on huge samples, and we can reproduce this within OPM with quantum sensing on the small samples. So now what do we do with it? We've done a fatigue test, meaning we have a lot of loading cycles on a pure iron sample, which you can see down here. And a few things here are happening. On the top, you can see the magnetic field as a function of stress. And we actually go like a cyclic loading. We go back and forth with the stress. And every time we go back and forth, we generate one of these magnetic hysteresis loops here. On the bottom, you can see the sample. This is after 10,000 cycles, which corresponds here to the black curve. And we can see here after 2.5 million cycles, which corresponds to the purple curve. On the bottom row, which is like macroscopy images of the sample, we can see that we see exactly nothing, which is also wanted, sort of. It just means that everything that happened in the material, like any fatigue process, any dislocation, emission, whatever happened, is not visible yet in any measurement technique that we have. But the magnetic field is changing already. So we can see here from the black curve, it moves sort of up to this level on top. It stays here for a while, and somewhere between 500,000 and 2.5 million cycles, the whole cycle shifts down. So the magnetic field is actually already changing, but we don't see it already in the sample. So now we want to investigate this because this holds potential, of course, and we want to exclude all of sort of influences that we have probably on the material. So we use the iron silicon from a single crystal, and we repeat this experiment. You can hear 10,000 cycles, 2.5 million cycles. The sample is a bit dirty, I have to admit, but technically it's still not damaged at all. So, but if you look again at the curves on the top, you can see it moves up, stays here for a while, and then moves down. Okay, so some sort of information about fatigue is encoded in this magnetic field. And the question is now, okay, what exactly is happening here at all? So what people usually do to investigate magnetic states in these samples is magneto-optic Kerr microscopy. It's like a standard technique. It's very known. And especially on iron silicon, this is very well known. We did this measurement together with Professor Rudolf Schäfer at IFW Dresden. And basically, we just took our whole tensile test apparatus, we put it in a car, and we drove it to Dresden, and we built it there under their Moog microscope. So what you can see on the right, you can see here this gauge area of one of these samples. We shine, of course, polarized light, and we depolarize because the light is interacting with the magnetization on the very surface of the sample. So we go here through our loading cycles, and you can see here the magnetic domains shown in black and white. They evolve in sort of a like wild sort of fashion. So and we were wondering, okay, what is going on here? So we have these tensile tests, which gives us magnetic field information. Then we see here the magnetism is actually behaving in a very specific way, which we cannot really pinpoint yet. So we investigated both of it. So we had here one of the tensile samples. We start here at 0 cycles. There's a residual stress layer from polishing on top. This is why we don't see any domains here. So and then we start going through the cycles up to 62,000 cycles. And then we see this pattern evolving. But in this case, it evolves to a certain pattern up to 60,000 cycles, and it's actually not much is happening. So if you have a look here at the top 2 parts, these belong to the green curves, and the bottom 3 belong to the red curves. So now there's a difference happening. So we have here, most of the changes happens between 60,000 and 62,000 cycles. And in the OPM, we have the green curves, which go to 15,000 cycles, and most of the changes happen now between 15,000 and 60,000. So the magnetic signal, which is generated by the whole sample in the inside of the part of the sample, it moves up and it stays at a certain level. And this is already happening here, where we don't see anything yet in MOOC. And then only on the end, this pattern on the surface is evolving. So the hypothesis that we have now is that between here and here, between here and here, most of the magnetic state is already fixed to some sort of damage. This means that the hypothesis that we have, like the magnetic field or the magnetization, is fixed in the center of the sample first, and the surface is only aligning in the end. So this gives us the information that the OPM, like the magnetic field in the OPM, holds information about the structure of the material before we can see it actually in the microscope. So let me summarize. First, part 2, we have the change in magnetic field, even there is no damage seen yet in the material. We have a magnetization pattern, which gives insight on how the material is damaged, where do we get the pinning. But we have one missing component, because in the MOOC we only see qualitatively the surface, and we get in the OPM a signal from the whole sample. So we have to bridge that gaps, and we do this with quantum sensing with NV centers. So we have now the ingredients. We have the microtensile sample, we have the testing with OPM, we have the MOOC, and the missing link are the NV centers. So let me show you how we do this. So all the NV technology is located at Fraunhofer IAF, and there are certain things. So we have two approaches. We have a single NV scanner, where it's like one single NV center located in a scanning probe tip. And we have a wide field approach, which is a dense layer of NV centers in a wide area of a diamond, technically. So there are certain technologies. There are actually the system of Konami, who are also here, and we have the system of QSaber. Both are available at IAF. And on top, we have this wide field microscope, which is developed at IAF at Fraunhofer, and it's also custom built. We have a demonstrator of this wide field microscope just around at our booth. Would be happy to see you there and maybe answer some questions for you. Okay, the first data I'm going to show you is from the wide field microscope. And don't think I have to explain a lot about NV centers in this occasion here. Anyway, we have the defect, like a nitrogen on the carbon side, and we have a vacancy next to it. And we align this and bring these together, and what we can see is that it develops quantum states, very discretized, in a ground state and an excited state, of course. And the NV ground state here is sensitive to magnetic fields via the Siemens splitting, and we can read it out with a green laser. And if we do this from the zero state, it shines very bright. If we do it from one of the plus-minus state, it's very dark. So the wide field itself, it's like we have the diamond with a dense layer of a lot of NVs. We shine the laser and we apply microwaves to shove around the spin between the states with a microwave antenna, which is just irradiated from the top. So the setup is diffraction limited, so we get down to whatever our optics allow us. And the diamond itself is CVD grown at IAF, and it's also irradiated with electrons. So the big advantage we get from this is fast scans. So with this wide field center, we sacrifice a little bit of resolution, but we get a scan on the order of 250 by 250 micrometers in like 15 minutes. So which is orders of magnitude faster, of course, than the scanning approach, but we sacrifice the resolution. So what we can see from this, this is like an ODMR spectrum, and the splitting is, of course, here between these two dips. We didn't calculate the absolute magnetic field in this case because this is an average of all NV directions in the diamond, which gives us more or less like an approach, like an average value only. So we left it here with splitting in case you're just wondering why there's no magnetic field. Okay, on the bottom, we have again the center part of one of our tensile samples after fatigue. So there's a lot of necking, a lot of plastic deformation. You can see again here in black and white, the magnetic domains are pinned to the damage somewhere on the surface and also in the rest of the sample. Now on the left, this magnetic field map here, splitting map is of course proportional to the magnetic field. We can see here certain features happening which are present in both of the pictures. We can see here the edges of the sample both in the dashed lines, and we can see a scratch across the sample surface, also in both of the images. So this is visible here in the magnetic fields, and we can see it here. But the most interesting part for us is we can reproduce what we see in MOOC, but we also have the additional information of the magnetic field, which now allows us to compare to the OPM measurements. So, of course, we would like to see what exactly happens maybe if you have a scratch like this or something, and if you have like maybe something like a cracked tip or something really small where the magnetization is pinning. We want to know what exactly happens at this specific point. For this, we did also scanning and V measurements. As we said, we have both of the systems available. For the data I'm going to show you, we used the Konami setup for no particular reason. It was just like the one we used. We can do the same with the QSaber, of course. But the data you're going to see is from Konami. So what we did, we have our tensile sample, and we fabricated a crack here on the side. So we did a small slash with a razor blade, then we fatigued, and then there's the crack evolving. And here on the very tip of this macroscopic part, there's a micro crack happening, which we don't see here. So now we go to the scanning system, and we scan over this red area here. Now we have different sort of plots that we can see. On the left one, it's the magnetic field as a function of position. On the very right one, it's an AFM plot, which you can measure simultaneously in the system. And in the center, there's a fluorescence plot. Fluorescence is interesting because any field that comes like perpendicular to the NV quantization axis actually kills the fluorescence a bit. So we can, from the contrast that we can see here, we can already see a little bit, is there a domain wall, is there fields happening in a wild fashion, or is it very linear? So, and on the top, on the very left here, you can see here this white line and the red line, which are sort of indicating that the magnetic field, like the domains here, stray field domains are a little bit changing. We can see here it's interrupted at some parts. And if we look here at the AFM image, it's already the same here. So it actually falls down. So it's a crack, it's like a topography change, and you can see it in the magnetic field. It's also happening here in the fluorescence image, not as clearly as in the AFM and in the field, but it's there. What's also interesting, we have these horizontal lines, and we were actually wondering what is that? What is going on here? So we went to analyze that a little bit further, and what we see, if we do line scans across the AFM image, on the top part we can go here to these vertical horizontal lines, 1, 2, 3, and we can see we have like steps of like 400 nanometers or something, which belongs to the crack tip. It's very characteristic. And if we want to look at these horizontal lines, we do the line scans in this direction, like these two, and we can see it's a very fine modulation of around like 40 nanometers, and over in a really like periodic fashion. So this is what we think typical for if we do polishing with a certain grain size, we leave these scratches. So, and this is actually a polishing residual, so it's leftover from the fabrication process. Main part, we can, with this technique, we can investigate topography together with magnetism, and we can sort of distinguish what is going on here. We can have these characteristic features, and instead of like coming up with models and to investigate everything, we just do the line scans, so we have both correlation to the magnetism and to the structure. So to summarize part 3, NV magnetometry gives us a stray field map and can be correlated to the domain pattern we see in MOOC. We can identify pinning of magnetism to damage, and we can investigate also features on the nanoscale using these scanning techniques. Big part, and also what we are working on still, is like we want to correlate the NV and the OPM signals. So we can have like sort of, say we have a drop in magnetic field in the OPM, okay, something happens, we go to the NV, we want to see what exactly is going on, we can have this magnetic field map and maybe see some pinning. Then I want to come to the outlook. We do some things beyond that. So at IPM, we thought, okay, but we have this high sensitivity of the OPM sensor, why not use it as a scanner? And to have a scanner, we need a flux guide system, which is nothing more than basically like a ferromagnetic part, which focuses the magnetic field from the sample here just to a small spot, and effectively it increases the resolution. So first data here are shown. We have weld seams on a sort of material, and we scan across the backside of this weld seam. So we don't scan over the weld seams, but on the backside. And if you weld, there's a structural change in the material, which changes the magnetism as well. And if we go over here, we can see from the magnetic field the location here of the weld seams in the dark spots. So also on IWM, we are going into micromagnetic simulations, which will help us to interpret like the signals from both the OPM and with the ENVIs. This is a very early stage, and we're exploring this further and further now. So for example, here, if we have like a material, like these line cuts through a material, and we have a cavity, something, or an inclusion in here, how does the magnetic stray field atop of this material over the surface look like? And if we scan above it, what do we see there? Okay, to summarize everything, we have quantum sensors for material science. They allow us to go from a macroscopic scale to a microscale. We have magnetic signals from OPM that can detect structural changes faster than we can see it in Vogue microscopy, for example. And we have ND magnetometry to go to nanoscale, investigate it in more detail, and correlate also to the OPM. So with this, I want to thank you for the attention. I would like to answer your questions if you like. You can also visit us at our booth just right behind the stage. And thank you a lot.